Welcome to the visit training session titled Utilizing Synthetic Imagery from the NSSL 4-Kilometer WRF ARW Model in Forecasting Cyclogenesis. My name is Dan Bikus. Dan Lindsay and myself put this together along with other folks listed down here at the bottom. This training session is part of a series that focuses on applications of synthetic imagery from the NSSL 4-Kilometer WRF ARW Model. In this training session, we'll consider applications of the synthetic imagery towards forecasting cyclogenesis. The main goal of this training session is to build on concepts from the previous visit cyclogenesis session, and for that reason I'm listing it as a prerequisite here. This particular session looked at a blend of satellite imagery, NWP output, and conceptual models, and learned to integrate all of those in a way that it could be understood within this training session. Now, in this particular session, for the NWP output, we're looking at the synthetic imagery and comparing that with the GOES imagery and understanding certain conceptual models that we learned from this initial training session. So for that reason, I'm strongly recommending that you go through that if you haven't already. Again, this training session will build on conceptual models that we learned from this particular training session, only instead of looking at NWP output in terms of, say, geopotential heights or other fields that we're used to looking at there, we're looking at the synthetic imagery. And the reason is the visual comparison between the NWP output and the satellite imagery is that much easier when you're comparing the synthetic imagery with the GOES imagery. The learning objectives will be very similar to the previous cyclogenesis session identified in the previous slide. The difference here is that we're applying these principles to the synthetic imagery rather than the GOES imagery. So to list the learning objectives here, we want to learn to identify cyclogenesis features we're familiar with in the GOES imagery in the WRF ARW synthetic imagery. This is an efficient visual comparison between model output and GOES imagery. In terms of specifically what we're looking at, we're going to mainly look at the airstreams that are related to cyclogenesis, not so much a comparison of QPF fields or those types of model output. We're looking at the cyclogenesis-related airstreams. So things such as the conveyor belts, looking at the dry slot or the dry conveyor belt, the warm conveyor belt, the cold conveyor belt, for example, looking at the location and timing of those. We want to identify the type of cyclogenesis because that's important in terms of following the evolution of it. And then from all that, we want to assess how much confidence we have in the synthetic imagery, in other words, in the model, in terms of the evolution of the cyclogenesis. Should you have more or less confidence in the forecast from that point forward when you're looking at the cyclogenesis event? Here's some background information on how the synthetic imagery we're looking at is produced. The model is run at NSSL once a day at ZeroZ. Certain model output fields, including cloud water, cloud ice, temperature, water vapor, etc., are sent to CIRA and SIMS. These WRF outputs are used as inputs to a model that generates the synthetic imagery. Gaseous absorption is calculated for cloud-free grid points, and modified anomalous diffraction theory is used to obtain scattering and absorption by the cloud particles. The model outputs brightness temperatures for a number of satellite bands. And for additional information about the details of the model, including how the synthetic imagery is produced, we do have references available on the student guide webpage if you're interested in learning more about that. Hourly output is generated for the 9 to 36-hour forecast, valid 9Z of day 1 to 12Z of day 2. Once a new model run comes in, it writes over to the 33 to 36-hour forecast, valid between 9 and 12Z from the previous run. The imagery is available to view between 10 and 14Z depending on the band. Keep in mind, if you look at this imagery in the morning time frame, you'll be looking much further into the future compared to looking at this in the evening, since it only goes out 36 hours. Some of the cases we look at in this training start at 12Z. These cases took place before we changed the first image to display to 9Z, and I'll remind you of that as we look at that, the various examples here. The bands are those that will appear on GOES-R, since the project is based on demonstrating products that will be available on the GOES-R satellite, scheduled for launch around 2015. The bands are very close to those found on the current GOES satellites, so that the principles discussed in this training session readily apply to operational GOES satellites of the present. Here's a comparison between the NISL WRF ARW water vapor synthetic imagery at 6.95 microns on the left, and GOES water vapor imagery at 6.5 microns on the right. Recall that the model is run once a day at ZeroZ. At the time, the new model run started at 12Z rather than what is done currently, which is 9Z. The early synthetic images between 5 and 11Z on the 1st of February, remember the times are down here, come from the ZeroZ 31 January model run, while those from 12Z forward are from the ZeroZ 1 February model run. This explains the discontinuity that we see, and I'll go ahead and show it right here between 11 and 12Z. So here's the image at 11Z right here, and there's the image at 12Z right here, and you can see that we have a new model run and that there's some differences there. So as you're looking at this, whenever you're looking at the loops, just be sure you know when the new model runs are coming, and you just remember that. One of the main differences between the synthetic and the GOES imagery is that the brightness temperatures are warmer in the WRF ARW model. This is a known bias that is primarily due to the wavelength being at 6.95 microns versus 6.5 microns, which would look lower down into the atmosphere and thus be warmer. Be sure to focus on features rather than getting caught up in brightness temperature differences. Another bias is the aerial coverage of the colder cloud tops that are typically underdone in the synthetic imagery. Given these biases, we can begin to look at important signatures related to cyclogenesis. For example, early in the loop, I'll go ahead and advance it to right here, we can see a baroclinic leaf in the Kansas, Missouri, Oklahoma, and Arkansas region. And again, just accounting for the biases here, that the imagery will show up a larger area of colder brightness temperatures in the GOES imagery compared to the synthetic imagery. But still, what you're looking at here is a baroclinic leaf, and that's the thing to keep in mind. The features that we're looking at that are related to cyclogenesis. A little bit after this, we see a dry slot that moves from Texas towards the northeast, towards Arkansas, and in time develops this familiar comma shape to the cyclone. The eastern portion of the comma shape corresponds to a warm conveyor belt, which you can see right here extending from the Gulf of Mexico northward. And again, just note the appearance of that in the GOES imagery versus how it would typically appear in the synthetic imagery, and that is the aerial coverage of the colder brightness temperatures will typically be quite a bit less than what you would see in the GOES imagery. One of the common forecast questions associated with cyclogenesis is what regions will be affected by the dry slot and when. We can pose the question in this comparison loop in terms of how well did the model depict the dry slot, just keeping in mind the bias of warmer brightness temperatures in the synthetic imagery. Another question can be how well did the model handle the deformation zone on the northwest flank of the cyclone. In other words, if you're forecasting up here in Davenport over to Sullivan or maybe Chicago here, and you're interested in this deformation zone that is moving through here, leading to a period of heavier snowfall for this particular region, you can make a comparison between the two here, and that would help you assess in terms of how much confidence you should have in that synthetic imagery from when you're presently looking at it for the future times here as well. And you can see in general that it appears to have done quite well here. The other thing that we consider is thinking back to our earlier cyclogenesis session, that we would refer to this as a basic type of cyclogenesis, and this seems to be depicted pretty well by the synthetic imagery as well. Let's look at another case. This is the 13 to 15 March 2011 case with the synthetic imagery on the left and the GOES imagery on the right, just as before. This is the water vapor imagery. So what we want to do here is compare the timing of the initial convective development from Kansas into Missouri early in the loop. So let's move on to the correct time here, and we can see this initial convection across Missouri and Kansas, and just go back and forth here between the two and find the corresponding. So again, keeping in mind the usual bias of the brightness temperatures being too warm in the synthetic imagery, and also the aerial coverage of the colder cloud tops typically is underdone in the synthetic imagery, but seems to be a pretty good correspondence there. The next thing we would look for is this area of convection from Arkansas into Missouri, again, how it would appear in the synthetic imagery, but it does appear to be doing pretty well in terms of the timing and the location of the convection here. And we notice also that after we see this convection, especially that first flare-up we talked about, the system really tends to wrap up here. In other words, take on more vorticity here across the central U.S. Now the next thing to look for is the development of a trowel. And remember, that would be the cyclonic branch of the warm conveyor belt coming out like so here. And you can see that across Missouri right here. And go ahead and circle it in the GOES imagery and the synthetic imagery. And in terms of the timing, it seems to be pretty good in terms of the timing, the location there, both pretty close over central to north central Missouri. And then we see another trowel develop. Let's go ahead and advance a little bit later, right here, where we see another cyclonic branch of the warm conveyor belt moving in this direction like so. And again, seems to be pretty good correlation in terms of the timing of that particular feature and also the location between the synthetic imagery, the forecast, and the GOES imagery that we see on the right. So I'll go ahead and let that loop here so you can see some of the similarities, some of the differences. And again, when you're looking at this, you're looking at the various airstreams to give you a sense of how much confidence you should have in that model forecast that you're looking at from that point forward. Let's go ahead and look at another case. This is from 25 to 27 December 2010. Again, it's the water vapor imagery, synthetic imagery on the left, and the GOES water vapor imagery on the right. Oftentimes when you're looking at a long loop like this, the first thing you want to ask yourself is, when does that new model run come in, and what are some of the changes that we see with that? So let's go ahead and look at that here. We'll go to the correct time, which is 26 December, and like I said, at this particular time, the change was between 11 and 12 Z. So here's the old forecast. This would have been from the ZeroZ run on the 25th of December, right here. And then this particular time is the new model run from the ZeroZ run on the 26th. And you just make some mental notes here in terms of some of the differences that you would see between the different model runs. And then as we animate this along here, we look for some of the major features. We see obviously this big trough on the East Coast, which is resulting in a forecast of this coastal cyclogenesis that's taking place across the eastern seaboard here. Now, in terms of some of the airstreams that we would follow for cyclogenesis, let's go ahead and stop that and look early in the loop. I'll go ahead and stop it right here. And at this particular time, we can see a cusp right here across South Carolina. Go ahead and draw in how it would appear in the GOES imagery over here as well. And that's an important thing to look at in terms of when we're away from terrain regions, such as we are here. We're over the pretty much a coastal area here, so terrain isn't playing a big role. But soon after you see a cusp, you can generally infer a surface low to be just east of that cusp, right along the edge of the warm conveyor belt. So in the GOES imagery, it would appear something like this right here. And that's useful information, especially for these coastal cyclones where you're wondering where the surface low is as it's just offshore. The next thing I want to point out is the development of the dry slot taking place pretty much just east or northeast of the cusp, right up through here. Go ahead and point that in the GOES imagery over here on the right. And it appears to be a pretty good correspondence here in terms of the location and the timing of this dry slot here. So if you're sitting up here in New York, New England area, Connecticut, you can look at this and get a better feel for the dry slot, how it's doing in terms of the timing and the location of that from the synthetic imagery. Go ahead and let that loop, and you can see that eventually that dry slot goes away here. It becomes wrapped up, so to speak. So recall from the cyclogenesis visit training session that the cusp can provide information on the position of the surface low, and this comparison can provide more or less confidence in the surface low position. And then the other thing that we looked at here was the dry slot for these cyclogenesis events, where terrain does not play an important role, such as a nor'easter case like we're dealing with here. So these are the kind of things that you can assess with the synthetic imagery. Let's go on to our next case. This is from 13 to 15 April 2011. This is the synthetic water vapor imagery at 6.95 microns. The early portion of the loop shows a short wave moving eastward from Nevada towards Colorado. Note that we're spanning multiple model runs here as we have a fairly long loop that we're looking at. Considerable convection occurs in response to this approaching shortwave over Kansas and Nebraska on the 14th. Soon after the convection, we see a large increase in the vorticity associated with the shortwave over western Kansas. Let's go ahead and look at that in detail. We have this shortwave that's approaching from Nevada towards Colorado, towards the east. And then we see our first indications of convection near the Kansas-Nebraska border right here. And soon after we see that, we see a fairly large increase in the vorticity. In other words, this system really appears to get wrapped up as we see that first round of convection, and then we have a second round of convection taking place right in here, and a couple notes to observe here. First, notice just before this first round of convection, kind of at the base of this shortwave down here in New Mexico, we can see an expanding region of warmer brightness temperatures. And then soon after that, we see that particular feature kind of moving in this direction right here. Here's the convection, and then we see additional vorticity, so this system really becoming wrapped up. And then later in the day, we see another round of convection right at the leading edge of this region of warmer brightness temperatures, and this actually corresponds to a dry line that's moved out into eastern Oklahoma and northeast Texas, where we see convection that's forecast to develop by later in the day and into the evening hours here. Here's the corresponding GOES water vapor imagery for 13 to 15 April 2011. And the first thing I want to point out here is this short wave that we were following from Nevada towards Colorado. And remember earlier I pointed out along the southern edge of that in New Mexico into Oklahoma Panhandle, right around this time, we saw an expansion of warmer brightness temperatures. And it actually shows up better here in the GOES imagery because of the warm bias and the synthetic imagery. It tended to blend in with the background a little bit more. Here it has a little bit more contrast, but we can see that feature right here just before the convection that develops in Kansas, and then we see this begin to wrap around back in this direction, which gives us the indication that this low is starting to wrap up, acquiring more vorticity here, and then We see the second round of convection along the leading edge of this edge of warmer brightness temperatures right here, which corresponds to the dry line. And then a little bit later in the day, we see that additional round of convection go in eastern Oklahoma and into northeast Texas. So if we look at that in conclusion here, that we see a number of features that look pretty similar to what we just saw in the synthetic imagery. Again, accounting for the biases, for example, the warm bias that we have in the synthetic imagery, just really focusing in on the various features that we're looking at for cyclogenesis purposes here. Our next case is from February 2 to 3, 2012. We'll start off with the synthetic water vapor imagery. And the obvious feature here is this large cutoff low in the west. The subtropical jet is situated southeast of this trough. And if we stop this and go to a particular time period right around here, we can see convection that develops in this particular region from southeast Colorado towards northwest Oklahoma, and that continues to develop in time here. This likely indicates the development of a warm conveyor belt. This warm conveyor belt becomes more organized in time here and result in considerable precipitation back here towards the front range of Colorado and also into southeast Wyoming, Kansas, and Nebraska further to the east here. I'll just go ahead and let that loop. It also provides more baroclinic energy for the system to work with as well. This eventually becomes cut off by the later portions of the loop by about 10Z on the 3rd. And I'll go ahead and stop at another time here later in the loop. And what we're going to look at here is nighttime convection that's firing here in Texas Panhandle into western northwest Oklahoma, and you can see that continue to persist and perhaps be associated with a new warm conveyor belt in this area. Note that we do go through a new model run between this time and actually between 8 and 9Z right here. We have a new model run. But generally it looks like this is associated with a jet that's coming through here at upper levels and associated with another warm conveyor belt that's developed. And this one earlier back here eventually became cut off by about this time here after it had produced a widespread area of precipitation in this general area right here. Here's the corresponding GOES water vapor imagery, and you can see good agreement between what we saw in the synthetic imagery and the GOES imagery here. The key to remember is our objective is the comparison of the various airstreams related to cyclogenesis between the synthetic imagery and the GOES imagery so that confidence in what happens next can be assessed. Now let's go to our last case. This is from January 25 to 26, 2011. We'll begin with the synthetic water vapor imagery. Initially, this appears to be a cold air cyclogenesis example. Recall from our visit cyclogenesis session that a cold air cyclogenesis example is one where we have a clear separation between the upper level low and the warm conveyor belt to the east. Now the exception here is near the end of the loop where it appears that we have some convection filling in between the warm conveyor belt and the upper low to the west here. And that's important to consider when you're following the evolution of the cyclogenesis, just keeping in mind what type it is that we're looking at. Now what I want to do next is stop this early in the loop and call your attention to this region right in here. And we can see it during this time. We can see a flare-up in the convection here between about 20Z and right here from Alabama towards eastern Kentucky. I'll just go back and forth one more time so you can see that here. It appears that we have the the warm conveyor belt becoming more organized at this particular time, we don't see a clearly defined cyclonic branch that wraps back around the surface low with this. So it doesn't appear to be a secondary warm conveyor belt. At this time, the comma head and deformation zone that we see appears better developed on the west and northwest flank of the cyclone, this feature right here. The dry slot, which we see coming in here, is forecast to move towards the mid-Atlantic region by the morning hours of the 26th, oriented pretty much like this here. The other thing I want to point out is the model run. You always want to be aware of when the new model runs are. At this particular time, they were coming in at 12Z. So here's 11 and 12Z, and you can see some differences here. Here's the latest here at 12Z. The biggest difference between the model runs appears to be the area of colder cloud tops across eastern Kentucky and West Virginia. Note that southern New England is brushed by the cold cloud tops within the warm conveyor belt, but then replaced by cold cloud tops in the deformation zone on the northwest flank of the cyclone by the later portion of the loop. Another key question while viewing this entire loop here is the phasing of this shortwave that we see moving like so across the Great Lakes region towards the southeast. And the question is, will that phase with the system of interest here, the coastal storm? And just by looking at this here, it appears that by the end of this we do get some phasing. And then another thing to give you some confidence, or at least something that makes sense in terms of the phasing of these two systems, is an intensification of the coastal low. And we can see that manifested by convection that's filling in here between the warm conveyor belt and the upper low to the west. And that would also give us indications that we have a transition in the type of cyclogenesis types from a cold air type of cyclogenesis to an instant occlusion type of cyclogenesis, which is a more intense type of cyclogenesis that's taking place here. Here's the corresponding GOES water vapor imagery. The overall picture is similar to that depicted in the synthetic imagery. Again, keeping in mind that it's the features, the larger scale features that are important here. We don't want to get too caught up in the difference in the brightness temperatures being warmer in the synthetic imagery versus the GOES imagery. Just concentrate on the various features here that are important for cyclogenesis. Next, what we're going to do is compare some various times to look more closely for some differences. Here we're going to do a comparison right at 12Z between the synthetic imagery and the GOES imagery. So what I'm going to do is just fade in between the two here. And what you would do here is just compare the position of the upper low, the warm conveyor belt, and also this approaching shortwave that we see over Wisconsin. And they all seem to be doing pretty well here in terms of the location. Again, don't get too caught up in the fact that the synthetic imagery is warmer, the brightness temperatures are warmer. Where we do see some discrepancies are over Virginia and Pennsylvania here in terms of the dry slot. Now, keeping in mind this could be attributed to the warm bias in the synthetic imagery. And what we can do to help answer some of those questions here, or at least other things to look at, are to overlay some model output fields. This happens to be the RUC. You can choose other models to look at here. This is the tropopause pressure. This would be lower where we have our upper low as we'd expect here, so looking for some discrepancies or agreements in here. Also, in relation to the shortwave that's approaching over the Great Lakes, how much phasing would occur later on. That's another thing that you can assess here. Also looking at a layer relative humidity. This is the 500 to 300 millibar layer relative humidity, which is generally where the water vapor imagery peaks at, right around that layer. And what you can assess here is the dry slot. And again, look for differences between the synthetic imagery and whatever model you happen to be looking at. Here's a comparison at 18Z. So similarly, we have our synthetic imagery, and then here's our GOES imagery, and we can just go back and forth between the two, look for any differences. Again, here's that important shortwave that's coming out of the Great Lakes region here. Notice that it does appear quite a bit more subtle due to lower brightness temperatures here in the GOES water vapor imagery, but it's still there, and that's the thing you want to keep in mind, not so much how it appears in the imagery, but the location of it and also the timing. And it seems to be pretty good here in terms of its agreement with the synthetic imagery. Another way you can assess that is you can bring up the relative humidity, or you can bring up the tropopause pressure to evaluate these types of things here. Finally, here's the ZeroZ comparison between the synthetic imagery and the GOES imagery. And as before, we can look for some areas where there's discrepancies and some similarities here in terms of following this cyclone along. So again, our objective is to compare the synthetic imagery with the GOES imagery here, and that would give us a better idea in terms of where we would have more confidence or less confidence in the various features and airstreams that we're looking at that are related to cyclogenesis. In conclusion, we identified cyclogenesis features that we're familiar with in the GOES imagery in the WRF ARW synthetic imagery. There are some differences, as we talked about, but if you stay focused on the various features here that are related to cyclogenesis, such as the conveyor belts, the location and timing of the conveyor belts, the type of cyclogenesis and how that's evolving, the evolution of the dry slot, and also looking at short waves and jet streaks that can lead to cyclone intensification. Comparison between synthetic and GOES imagery, using that to assess confidence in the evolution of the cyclogenesis from that point forward in the forecast time. Where can you view the synthetic imagery? It is available on AWIPS via the LDM. It's part of the GOES-R Proving Ground products. And if you're interested in getting that on your AWIPS, just contact us. Our contact information is on the next slide. If you want to look at this on the web, you can see on the CIRA webpage, it's right here. On the SIMS webpage, it's at this URL. And if you're interested in the model output fields from the WRF ARW, that's available right here. Here's our contact information. If you have any questions or comments, just let me know.